In this video, we will be looking at Laplace transform. Laplace transform has numerous applications in circuit analysis, in signal processing, control systems, various aspects of electrical engineering and mechanical engineering, and even beyond. Laplace transform basically transforms a time domain function to a complex frequency domain function. Now, this is the basic expression of Laplace transform. So let's just break this expression down for better understanding. Now, this sign here denotes the Laplace transform, and this f of t is in curly or brace brackets. You can see this is called brace bracket or curly brackets. So now f of t is just a function of time, or the time domain function. Now you can see f of t just like f of x, f of y is just denoted by small letter f. Now the Laplace transform, like we said earlier, converts a time domain function to a complex frequency domain function. Now here you can see the function here, f of x, is capital letter F. It's a complex frequency domain function. All right, so now S here, yes, we call it S domain. It is a mathematical domain that represents complex frequency function. All right, we'll be solving some examples afterwards, so let's just basically define these terms. Now, exponential raised to power minus st is an exponential decay factor as it relates to this equation, or the definition of Laplace by this mathematical expression. F of s is a transformed function in the S domain, that is the complex frequency domain function. Beside the application of Laplace transform in circuit analysis and so on and so forth, it is also a very, very useful tool in solving linear differential equations. All right, it is important to mention that there are common functions associated with Laplace transforms. The ability to identify these unique functions would help in solving problems related to Laplace transforms. And these common functions are unit step function, ramp function, exponential function, sine function, and cosine function. Of course, there are more, but this is the few and the major ones we will be considering in the next couple of slides. All right, let's look at unit step function. When it comes to unit step function, it can either be in the standard unit step function form, that is u of t, or it can be in a shifted unit step function, that is u of t minus a. In the standard form, a equals 0 in the standard form, whereas in the shifted form, a is greater than 0. Some other things you need to know about both, talking about the standard unit step function and the shifted unit step function is the definition. Now, this is the definition of the standard unit step function, and this is the definition of the shifted unit step function. By this definition, the function is 1 for t is greater than or equal to 0, and 0 when t is less than 0. And for the shifted unit step function, we have that a is not equal to 0, and that means that the function steps from 0 to 1 at t equals a. That's it steps from 0 to 1 when t equals a. All right, let's just move on. Now, by the definition of Laplace transform, a unit step function is defined by this is the function f of t ordinarily, but because it's a unit step function, it is denoted in this form. So now the Laplace transform of a unit step function equals, now basically the definition of Laplace transform is integral from 0 to infinity of exponential raised to power minus st dot function of t dt. Now this time around we are talking about u of t, and here the coefficients of u is 1, so that is why we've got 1 here. Now integrating this via just basically integrating this results in the Laplace transform of this unit step function equals 1 all over s. Just do the integration and consider the limits. Just take the boundary, the limits from 0 to infinity, and you'll get this. Now, this is the general Laplace transform of a unit step function. Now, for a shifted unit step function, this is the general equation. Now, this general equation must be known in order to solve problems related to unit step function. Now, take for example, find the Laplace transform of f of t equals u of t minus 3. Now, the appearance of this transform, this Laplace transform, or this function, shows that it is a unit step function. In this case, it is a shifted unit step function. Now, how do we know? Because it's basically conforms to the shifted unit step function. So in order to solve this, we here have to identify that a equals 3, just relating the general form with the function we have before us to solve. So just relating this, we find out that a basically equals 3, and from the general solution we basically substitute 3 for a in the general solution. So the Laplace transform of u of t minus 3 equals exponential minus 3s all over s, and that is the answer. It's just as simple as that. Now let's consider another example. Find the Laplace transform of f of t equals 4u of t minus 2. Again, this conforms to a unit step function, of course, the shifted unit step function in its expression, in its appearance. So in order to solve that, we have the general concept here, and from the question or from the example given, we can relate these two guys here, and that will mean that A equals 2, and we can treat this as a constant. So, and in other words, the coefficients of u is 4, and that will mean substituting 2 into for A in this solution, and having this 4 as our constant, so that just becomes 4 as a constant multiplied by this solution that is exponential. In this case, A equals to the exponential raised to power minus 2s all over s. And when we multiply that out, that gives us 4 exponential raised to power minus 2s all over s. And that is the solution to this problem. All right, next we look at ramp function, and let's do that together with Laplace function of the power of t, that is t raised to power n. We need to do that because basically they can be solved in the same way. The basic ramp function is given by, that's the Laplace transform of a ramp function is given by this expression, and that could be seen as the Laplace transform of t to the power 1, that is t raised to power n, and that will give us basically the Laplace transform of that, which is a ramp function, will be this expression. However, okay, let's just define the ramp function. It is defined as a function of t equals t, and that is why we can regard that as t raised to power 1, and it basically represents a linear increase over time, and it is commonly used in signal processing and control theory to represent systems that experience a steady change. Now remember the definition of Laplace transform, and when a function of t is simply t. So just using integration by parts will of course taking note of the limits between 0 and infinity, then the Laplace transform of t basically becomes 1 over s raised to power 2, and this is a ramp function. In the same vein, the Laplace transform of the power of t, that is t raised to power n, is given by this expression, that is Laplace transform of t raised to power n equals gamma open bracket n plus 1. And because this is a gamma function, this expression is the same as n factorial, so all over s raised to power n plus 1. So now this is the Laplace transform of t raised to power n, and considering this general form of the Laplace transform of the power of t when t equals to 1, you see that the expression becomes that of the general Laplace transform of a ramp function, that is 1 all over s raised to power 2. All right, so now this example basically relates to the ramp function. Find the Laplace transform of a function of t equals t. You see the question takes the form of a ramp function or the Laplace transform of t raised to power n, or the power of t. So and basically noting down the general form of the Laplace transform of the power of t, which is this, and basically substituting 1 for n will result in the Laplace transform of t being equals to 1 all over s raised to power 2. This is practically true. Now the second example, let's look at now determining the Laplace transform of f of t equals to t raised to power 4. So this constant here, these two here, we treat it as a constant. It is just a scaling factor. And when we look at this expression, it takes the form of the Laplace transform of t raised to power n. And so we basically apply this general rule in solving for the Laplace transform of this expression. So now, solution. The Laplace transform of t raised to power n is, so we first of all write the general solution of the Laplace transform of the power of t, and that gives us n factorial all over s raised to power n plus 1. So now in this case, n equals 4. And so we just simply substitute for 4 for n in this general expression, and taking 2 as the scaling factor and just treating that as a constant. So now what we then get is the Laplace transform of 2t raised to power 4 equals 2 multiplied by the Laplace transform of t raised to power 4. So Laplace transform of t raised to power 4 is 4 factorial all over s raised to power 4 plus 1. Now 4 factorial simply means 4 times 3 times 2 times 1. That is 4 factorial. Now 4 times 3 gives us 12, and 12 times 2 gives us 24. 24 times 1 remains 24, and that is how we got this. So all over s raised to power 5. Of course, 4 plus 1 is 5. Now we can now substitute 2 back into the expression. That is the scaling factor of 2, and the Laplace transform of 2 t raised to power 4 becomes 2 multiplied by 24 all over s raised to power 5, which gives us 2 times 24 gives us 48. So the answer becomes 48 all over s raised to power 5. All right, next let's look at the Laplace transform of an exponential function. So for the exponential function e raised to power at, where a is a constant, the Laplace transform is straightforward to calculate. In other words, by the definition of Laplace transform of e raised to power at equals integral from 0 to infinity exponential raised to power minus st. So the function of t basically is what is here, and this is that function of t, that is exponential raised to power at dt. So now this equals, because we've got the same base here, we can simply add the power, and that is what we've done here. So that gives us the integral from 0 to infinity raised to power e raised to power minus open bracket s minus a close bracket t dt. So now evaluating the integral basically gives us the Laplace transform of e raised to power at, and that is 1 all over s minus a. So that is for s being greater than a, it must be in this form. And basically, this is the general exponential function of form of the Laplace transform. This is the general expression for the Laplace transform of an exponential function. And this is very useful in solving ordinary differential equation involving exponential growth or decay. All right, let's look at some examples. Now, example 1, find the Laplace transform of f of t equals exponential raised to power 3t. Solution. Now, knowing that the exponential function, the Laplace transform of an exponential function exponential raised to power at will equal 1 all over s minus a, provided s is greater than a. So relating this general Laplace transform of an exponential function to this equation, we will be able to identify that a equals 3. A equals 3. And of course, this, by me looking at this, it takes the form of an exponential function. So we basically use the general rule, the general form or solution to determining the Laplace transform of an exponential function in solving this problem. So now, as a has been identified to be equal to 3, so what we then do is just simply plug, substitute 3 for a in the general solution for the Laplace transform of an exponential function. So that is Laplace transform of exponential raised to power 3t equals 1 all over s minus 3, and that is the solution. Now let's look at another example. Find the Laplace transform of f of t equals 5 exponential minus 2t. Now we treat 5 here as a constant. Basically it is a scaling factor, so we just treat it as a constant. Now solution here. Now relating, of course, this is an exponential function, and the Laplace transform of an exponential function is given by this expression. So comparing this expression and this shows that a equals minus 2. And when we substitute minus 2 for a in this equation, it becomes easy to determine the Laplace transform of 5 exponential minus 2t. And that basically gives us 5 multiplied by 1 all over s minus 2. So minus times minus simply becomes plus, and that is how we got this. So 5 times 1 gives us 5 all over. So we simply just write this s plus 2, and that is the answer to finding the Laplace transform of the function of t here. So next we go to Laplace transform of sine and cosine functions. So let's start with sine functions. For sine at, the Laplace transform is given by, according to the general definition of Laplace transform, so that is the integral from 0 to infinity, exponential raised to power minus st dot sine at. So what we do here is just use integration by parts, and when we integrate these, taking the limits from 0 to infinity, the Laplace transform of sine at becomes a minus a all over s raised to power 2 plus a raised to power 2, and that is when s is greater than 0. Now this is the general form of solution for the Laplace transform of a sine function, and that must be known. Now with the knowledge of this, we can go ahead and solve Laplace transform functions related to sine functions. For example, find the Laplace transform of a function of t as a function of time, which equals sine 2t. Now this is a sine function, and the Laplace transform of a sine function is given by this solution. Now relating this sine function to this general solution shows that a equals 2. Now just substituting 2 for a in these expressions gives us 2 all over s raised to power 2 plus 2 raised to power 2, and that equals 2 all over s raised to power 2 plus 4. Now that is our answer. Okay, another example. Find the Laplace transform of f of t, a function of t, equals 4 sine 5t. Now this 4 is just a scaling factor or a constant, so we treat it as such. Now the solution, now relating this sine function to this expression shows that a equals 5. Now substituting 5 for a shows that the Laplace transform of 4 sine 5t equals, the scaling factor must be represented, so that will be 4 times then the Laplace transform of sine 5t. So now substituting a for 5 for a in the solution as we've got here becomes 5 all over s raised to power 2 plus 5 raised to power 2. So 5 times 4, 4 times 5 gives us 20 all over s raised to power 2 plus 5 times 5 becomes 25, and this is our answer. All right, next we look at cosine function. So for cosine function, the Laplace transform is similarly calculated relative to that of a sine function. All right, now the Laplace transform of cosine of at equals, by general definition of Laplace transform, is an integral from 0 to infinity, exponential raised to power minus st dot the function of t dt. Now the function of t here is cos at. Now using integration by parts and taking the limit from 0 to infinity, the Laplace transform of cos at becomes s all over s raised to power 2 plus a raised to power 2 for when s is greater than 0. Now, this must be taken note of as the cosine function, or the Laplace transform of cosine function. Now, bearing this in mind, we can also look at some examples. Now, find the Laplace transform of a function of t equals cos 3t. Now, relating this with the general solution for determining the Laplace transform of a cosine function shows that a equals 3. So now, by substituting 3 for a in this equation, general solution of the Laplace transform of a cosine function, then the Laplace transform of cos 3t equals s all over s raised to power 2 plus 3 raised to power 2. Now 3 raised to power 2 is 9. So that gives us this solution answer. Now let's look at another example. Now, if we are to find the Laplace transform of a function of t equals 7 cos 4t. Here, a is equals to 4. Of course, this is a cosine function, and the solution for the Laplace transform of a cosine function is given by this expression. So now this is just a scaling factor, a constant, which will be treated as such. Now, substituting 4 for a in the solution for determining the Laplace transform of a cosine function, we simply get this. That is substituting 4 for a in this equation. So we have s all over s raised to power 2 plus 4 raised to power 2 times 7. So 7 times s gives us 7x all over s raised to power 2 plus 4 times 4 gives us 16. So the Laplace transform of 7 cos 4t equals 7s all over s raised to power 2 plus 16. All right, these transforms shows the summary of the common Laplace transforms. There's the transform for sine function, cosine function, exponential function, ramp function, which is this, and we also considered in connection with the power of t, or the Laplace transform of t raised to power n, which is this, and we considered the unit step function and a shifted unit step function. So, and this is the Laplace transform of a unit step function and the Laplace transform of a shifted unit step function.